Malin. Så.
Är vi igång?
Alldeles strax. Yeah.
Okay, good morning and welcome to the breakfast webinar at ITRL. The slide disappeared.
Yes. Sorry.
But before we start, I would just like to ask you to keep your microphones muted and use the raise hand functionality in Zoom if you want to ask questions later. We will ask questions after the seminar. Keep your camera turned off unless you want to speak in the end, then you can turn it on. And this is a seminar by Gustav Wikström from Ericsson about
Hello.
the point of 6G. And
Exactly.
for us, it's very interesting to understand how 6G can be used for transportation and for vehicle technology. We're happy to have you here. And yeah, then I leave the word to Gustav.
Okay, thanks a lot. I will try to give some hints about 6G and transportation, but that's not my typical field of business. But we're looking at all sorts of interesting applications for 6G. Now we'll just get this sharing started. Are we live? Right. So Gustav Wikström, that's my name. I work at Ericsson Research, working now primarily with 6G since 2 or 3 years. And I will talk about 4 things, all related to 6G. First, try to hint a bit about when we will have 6G, when we're working with 6G. And then say broadly what 6G is about. What is the key features of 6G? And then I will try to explain what the point is. Why are we doing this? Why not stick with 4G and 5G and the older Gs? And in that green box, I will try to talk about the transport-related applications. I hope you find that interesting. And finally, I will say something brief about how we do 6G. But since this is not really a seminar about radio technology and networking technology, so I will not say so much about that. But if you have questions, I'll be happy to answer those on the actual networking technology. But otherwise, I will speak mostly about applications today. Okay, first, when is 6G? Yeah, if we look at the other Gs and the evolution of mobile networks, we have had a G more or less every 10 years. In 1980, we had 1G, 2G in 90, 3G came in about 2000, 4G in 2010, and 5G in 2020. So that's not completely true. We had it slightly before, but that's the sort of the broad commercial breakthrough of 5G. And then you could sort of guess when 6G would happen. It's about in 2030. That's what everyone is sort of thinking right now. And then you have these different bubbles surrounding the Gs, trying to place them in some sort of focus of the G itself. So if 4G was about the smartphone and the app economy, the smartphone came around 2011, right? So 4G was a lot about broadband applications, video, etc. 5G was a lot about, or is a lot about industry, digitalization in industries, also digitalization in society. A lot about IoT, Internet of Things. 6G, we think, will be about cyber-physical interaction, and that I will talk a bit more about. And where we are now, we are sort of in between 5G and 6G. We're still working on 5G, on something called 5G Advanced. That's the evolution part of 5G. And we're bringing in learnings from deployed 5G networks and the 5G evolution that's happening in standardization now. We're looking at lab tests, and we're starting to work with 6G then in trials. That will not happen yet, but we have started with lab tests, test benches, etc., proof of concepts, and then we will move into standardization in a couple of years. And by 2030, we believe that we will have the 6G commercial networks live. So that's where we are. And I can just say something briefly about here, the y-axis here. Maybe you wondered about that. What is that? Yeah, so you could see that as the scale of networks. How many network nodes do we have involved in the networks? How many connections do we have? So the scale of networks is increasing. The theme of the network, what you can use the network for, that is changing. But you could see this as a continued evolution of the network technology. And right now we are somewhere in between 5G and 6G. Okay, so what is then 6G about? Yeah, we have identified some needs that we see that we need to work on in the 2030 world. First, we have trustworthiness. So there is an increasing need of trustworthiness in society and industries, among operators and among end users. So we need trusted communication and computing for industry as well as society. And we need to provide critical information. So services that rely on critical information, that needs to be provided through the networks. And you may think that this is something we have already. Yes, but we will have even more of it, and we will have it in a wireless way, not only over fiber networks. Then sustainable world is kind of obvious by now. We need to make sure that networks are part of enabling a sustainable world. And of course, the networks themselves should be sustainable. We need to work with the energy consumption, and we need to work with use cases that help other sectors reduce their energy consumption and make them more sustainable in general. And it's a very broad topic and a very broad goal. That's of course something we need to work on with networks. Simplified life. So you could think of what you could do. Imagine what you could do for your own personal life if you have AI available more or less everywhere. So you have artificial intelligence that can help you in your everyday life, making decisions, optimizing things for you. And then you can think about doing that for society and for industries as well. So it's all about optimization, giving assistance, and providing efficiency throughout society. So that's also a need. And finally, application demands. We see that there are a lot of new services that start now, and we know from history that there are a lot of services that we don't even know about, that we haven't seen yet. Think about 4G and when the iPhone came, and people started to think about what the iPhone would be used for, and people would not have guessed what the iPhone is used for 10 years later, right? There's so many new services popping up every day. And we know that this will happen in the future as well. There will be a lot of new services, and they will demand more and more from the network. So we need to dimension the network so that we meet these application demands before they actually appear. So there will be new services that require extreme connectivity performances from the wireless network. Okay, so now we are in 5G, and I don't know if you have seen these type of figures before, but 5G usually is described as being about 3 different areas: mobile broadband, EMBB, enhanced mobile broadband, URLLC, ultra reliable low latency communication, and MMTC, massive machine type communication. And this is something that is being worked on and extended even further. So we are now in 5G advanced, and we add sort of a plus or 2 on these services and try to make them even better to address even more use cases. For 6G, we see that we probably will continue this development. We will continue to expand in these 3 dimensions: mobile broadband and different IoT flavors. And that's the center triangle here. And that's sometimes called INT 2020. That's the ITU version of it. We will expand that even further, and we talk about immersive communication. That's sort of the continuation of mobile broadband. We'll talk more about that, what it means. And massive communication, the continuation of MTC. So you could think of IoT, Internet of Things. And critical communication, the continuation of this ultra reliable low latency communication, but taking on the service level, not only on the link level. How can we provide services that are resilient and robust on all levels? And adding to this, we have 3 other triangles, and maybe it's hard to see here in the room, but they say AI compute, sensing information, and sustainable efficiency. So these are sort of 3 new dimensions that we want to add to this original triangle. So we want to continue enhance 5G in 6G, and we want to expand in 3 new dimensions. And I will talk a bit more about these 3 dimensions, what they are. But this is broadly what 6G will be about.
Sorry, can you immersive communication?
Yeah, so here I have some more details on what I mean. So we have these 3 corners: immersive communication, critical communication, and massive communication. So we see immersive communication as an expansion on mobile broadband. And here we want to provide really high rates as well as low latency, so that we can, for instance, enable holographic communication. So that's being able to provide really good service, really good quality of service beyond what mobile broadband can do today. Mobile broadband is, sending data packets now. There's no sort of clear latency control of these data packages. So we want to make this more tight in a way so that you can receive big data packets at a steady pace, and that's what you need in order to deliver holographic communication. Critical communication, we want to go away from this local scenario with the radio links that we control to a very high degree, and we want to provide wide area latency optimizations. We want, for instance, then transport related use cases. We want to be able to control latency in a wider area, like in a city, and not only in a factory hall. There's a lot of challenges related to that. And we have these two broad missions here in 6G. We have this communication focused corners. So these are the expansions of the corners here. And then we have something new, and that's what we like to call beyond communication services. So we want to, with 60, we want to do something more than just providing a very good bit pipe. We not only want to transport data, we want to make data. We want to be a data source in ourselves, and we want to process data. We want to do sensing in the network itself. So use the network nodes to sense the surroundings, and that in that sense to be a data source in itself. And we want to have computing services in the data so that we can process data, any type of data, and we want to add AI capabilities throughout the network, so we can offer AI-related tools to applications and to the network itself. So this is something more than just communication. So what we want to do is make 60 a sort of a network platform. So we say that we want to make it a platform for communication and beyond. So 60 should, of course, provide communication links, but we also want to provide computing, AI, and spatial data. So that's something we add. So we want 60 to be a platform, a versatile platform, for any type of service that needs high performance communication. That's obvious that we have in 5G, so that's a continuation of what we do in 5G. We will, of course, want to support mobility and non-local coverage. That's why we have cellular networks to begin with. It's to provide mobility and non-local coverage. Otherwise, we could just be happy with Wi-Fi. But Wi-Fi is not great for mobility. It's not great for wide area networks. And of course, cellular networks are great for providing security, resilience, and ensuring privacy. And that's something we see that we need to work more with, be even better with, and provide new levels of privacy, for instance, for the new services that are popping up. So this is what we see that we should offer. A 60 platform providing a lot of services related not only to communication, but also beyond. Okay, so that was sort of what 60 will be about. We want 60 to be a platform. And then what's the point with that? You may wonder, why are we doing that? Who's asking for that? Is not 5G enough? That's the most common question I always get. Why don't we just stop? Why don't we just stop developing networks now that 5G is so great? Yeah, so I mentioned that the sort of theme for 60 that we imagine is cyber-physical interaction. So we talk about connecting a cyber-physical world, and that sounds very sci-fi-ish, and it is in a sense. It is about wireless metaverses and digital twinning, but it's also more than that. So we have a physical world. In the physical world, we imagine that we will have lots of connected sensors, lots of connected actuators, and they send information and they receive information from a digital world. In the digital world, there you have intelligence, you have different processes, programs, knowledge, and you use the information from the physical world to update a digital representation in real time. And it's the network platform that makes sure that this happens. So the network platform connects the physical world with the digital world. And that platform should provide intelligence, connectivity everywhere, and be able to synchronize this to at real time. And that we call the CyberPhysical Continuum. And we have lots of different use cases that we can do in this CyberPhysical Continuum. One thing that is very cool, I think, is that once you have this digital representation of the physical world, you can simulate what will happen based on what has happened, right? So you can do predictions more or less in real time get sort of a very good picture of what will happen in the near time scale, and perhaps what will happen in the slightly longer time scale. What will happen in the traffic, what will happen in the network, and so on. And you can also trace back and see what did happen, what went wrong, if anything went wrong, and then you can analyze that and learn from it. Also, what's in 60 is that we see that we want to connect every part of the world, more or less. And that's our ambition. So the CyberPhysical Continuum will rely on a lot of wireless links. We need a 60 networks to connect these worlds, the physical world and the digital world. And you need a very flexible network built up by many different access types. So here you see in this very nice illustration, you have satellites, planes, drones, and you have different mobile nodes on buses, nodes on ships, you have satellite dishes, you have small nodes, you have tower nodes, you have devices of many different kinds, and they all sort of link to each other in this mesh type network. So there are many possible 60 links, and that gives a lot of possibilities in that you can reach everywhere with this one and the same network. Sometimes it's called network on networks. So you have sub-networks that are connected to a bigger network. That's in the end then connecting the physical world with the digital world. So I will not say so much more about networking, since this is not what you're here for. But a lot of the challenge lies in this connecting things. Okay, so what's in this cyber-physical continuum? Why use these very big words? Is there something for us? What's the point? Yeah, so I talked about these three different variants. Merged reality, that's immersive communication. Massive digital twins, that's massive communication. And situational awareness, that's critical communication. So here are three examples. Merged reality, you will be able to talk to holograms. You will experience things at a distance, for instance. You can watch a concert from home. You can work from anywhere. So it's connecting you with a distant scenario or a distant person. And you should be able to experience that as more or less reality. So that's merged reality. So you merged a digital object, a hologram, with your reality that you see around you, and you merge it so that you it feels natural. Massive digital twins, yeah. So you can, for instance, imagine connecting a construction site. So you place wireless tags on all the equipment and all the material, and you can track them in your digital model of the construction site. So you have your drawings, your charts. You know the material status. You connect to the logistics chain, and you can plug in all kinds of different ecosystems. You have local networks, of course. You have a Wi-Fi network. You have a Bluetooth network, etc. And you can plug them into this network platform then, and be able to merge all the data and control all the system on one platform. So here you can have a very good overview of what's going on, and you have detailed control. And then finally, situational awareness. So that's very interesting for you that work with transport. So you should be able to get an understanding of the physical surrounding around a network node. You should be able to locate objects that are not connected. You should be able to guide robots and vehicles with digital maps provided by the network. And you should be able to interact with cobots or collaborative robots. And that's all based on understanding the physical surrounding. So creating a map of the physical surrounding and updating it in real time. So now I have 3 more transport related usages. So first, you can think of remote cargo. So you can imagine working from home with a cargo bay or something like that. So you should be able to control a robot connected to you at a distance that in turn work with the cargo, right? So remotely move cargo using cobots. And cobots are these collaborative robots. You should be able to work from anywhere. Should not be connected to a sort of a distance. You should not have to sit in the next room. You should be able to have like a lights out factory where you sit on the other side of the planet, more or less. And this is difficult, right? Because you have to sense the scene remotely. You have to create a digital model of the scene. It's difficult because you probably want to have tactile feedback. So when you sit at home and you steer this, if you do it that way, right? So if you maybe steer a robot arm from home, you want to feel, you want to get feedback from the touch of the robot, right? And that requires a lot of speed from the network. So you need low end-to-end latency. Then you probably want to plug in an AI to help out with automation. You should not do everything remotely. You should do it autonomously. Then you need to trust the AI, right? So it needs to be an integrated AI with a lot of security checks in it. And then you need high rates for monitoring and control. You need a lot of video streaming. You probably need local sensors. And that's a lot of data to ship back and forth. And then we have a set of technologies that we're working on. So joint sensing and communication, it's a very trendy topic. So using the network nodes that you use for communication, you also use that for radio sensing. So more or less like radar functionality in the network nodes that you deploy. And of course, you want to integrate AI and compute. That's something I talked about. So the network infrastructure itself should be a compute facility and an AI facility. And then you probably need very dense network deployments in order to have this high precision, in order to have the support these high rates. So you need something like distributed MIMO, so small antennas that are distributed in the scenario. So in the cargo bay, then, for instance, you would have probably several different nodes, separated nodes that are connected to the network, and that can provide very good, very high rates and good precision. That's one such example. In this massive digital twin area, we can think of something called everywhere logistics. So you want to track and identify items on a global scale. So that could be different types of cargo, right? And you want to locate assets locally. So if you have a warehouse, you want to be able to check at any time what items do we have in my warehouse. So this is challenging from several perspectives. First, you need devices that are cheap, small, and that you don't need to manage a lot. So you need some sort of like a tag that you can put on any item, any piece of cargo that you can locate and that can send its identification on request. So there's a lot of technology related to battery and management of devices, and there will be very many, right? You can't manage them individually. And then current networks, they have a limited coverage, right? You can't cover the oceans, you can't cover Sweden even. So you need to expand the scope of networks, cover more areas and things. And then if you do that, if you want to cover everywhere, all of the world, and you imagine that you have very many nodes, very many devices that you need to track. What will there be will there be a very high energy cost in doing that? Will you waste a lot of energy by tracking all these devices? You need to do this in a energy efficient way somehow. Yeah, so for this challenge, we are then working on a set of technologies. So I think the three most important ones here are what we call zero energy devices. The devices that basically harvest energy from the surrounding. They're very small, cheap, and simple, you could say. So they harvest, for instance, solar power or vibrational power or thermal power. Things that you would have in your warehouse, for instance. And they would then not require any battery, and they could send data, yeah, say every hour or once or 5 times per hour, but not every second probably. There's not enough energy to harvest them. So that would be used for asset localization. So they maybe send a ping on request, and you localize that ping and you know where they are. And then you can build something like an asset digital twin, right? So you build a copy of your warehouse with all the stuff inside it. And then for global coverage, if you think about it, it's only one reasonable way of doing it, and that's through satellites, right? So there's this, I'm sure you've heard of it, LEO satellites, low Earth orbit satellites. So there are now several different flavors of that being deployed. And they provide excellent coverage. Not that high rates, of course, and the capacity is limited, so they wouldn't really compete with terrestrial networks in cities, but in a remote scenario, like in the oceans or in the rural areas, they are excellent for providing the coverage that you need. So we really need to integrate them into the networks, and there are several projects ongoing working with that. How you tie them into a sort of a network web of different links. So what I talked about before, this mesh of different networks links. You also need to have the satellites as part of that mesh. So that's already ongoing actually. And then you probably need to have something like multi-hop functionality, so that you hop between different network nodes over relays, and maybe even between devices. So maybe a tracker on one piece of cargo can relay to another piece of cargo. Maybe not in these zero energy devices, but if you have slightly more advanced devices, maybe on a ship, you would relay the cargo from on that ship over a node that is then relayed over satellite. So you have these multi-hops that you go through before you reach the sort of the endpoint, the intelligent network that is sort of capturing all this and analyzing it and representing it in some smart way for you to use it. Everywhere logistics. So that's also transport related. And finally, situational awareness about understanding a scenario. I think this is very related to transport. So the situational awareness in itself is transport related usage. Here, we want to have real-time understanding of objects and vehicles. And of course, vehicles can be connected. Objects are typically not connected. People are sometimes connected, but not always. Bikes are not connected. And the trees are not connected. Right? So connected objects, that's easy. That we can do already now, right? We can build a digital twin of all the connected objects in a city. But the unconnected objects, that's more tricky. So that could be, of course, the physical surrounding, the houses, the streets, etc. And that's static, that you don't need to update that often. But then you have people and you have things moving around in a city. So you want to have a real-time updated understanding of objects and vehicles in a city. And you want to be able to navigate robots in this scenario. And that could be then drones, other vehicles that are remotely controlled, or they are maybe autonomous. So they move around in this future scenario. And there are several challenges here as well. So today's networks, they have kind of spotty coverage. You cannot be sure that you have a connection in every spot in the city where you would need it. The availability of networks is varying. So you cannot be sure that when you move around that you have contiguous coverage. Maybe you lose connection at some point. And the energy performance is not good enough, simply, on networks. And the reliability and the latency of over-the-top compute services is probably not sufficient. So you can, of course, already now collect data from different sensors in drones. You could ship them over the top just as data packages and then analyze them on some web server, get some map back and use that. That probably would work to some level, but the total reliability of such a model is probably not sufficient to be able to trust it completely. So you need to integrate this into the 6G platform, and there you can have control of all the different steps. So also the compute and the distribution of data needs to be controlled. And relying on onboard sensors, you can do that today. You can equip a drone with lots of different sensors, like cameras and radars, etc. And that's possible, but it's heavy, and you don't really know what these sensors are capable of always, and they drain the battery. And it's kind of expensive to rely on your own onboard sensors. So it's better to use the sensors that are available around you. And maybe not only that, maybe you will still have some onboard sensors, but at least you can benefit from the sensors around you. So you want to be able to see around corners, etc. And there you can use the sensing information that is available around the corner, upload it to network, where you build this connected map of the city that is updated in real time. And for this, again, you need joint sensing and communication. You want to use the rather dense network that we foresee that we will have in cities. You want to use that to measure the surroundings and sense the physical environments around the nodes. You probably need multipath connectivity, connecting to multiple points in the network at the same time to be able to ensure that you have connection always. So when you are a drone and you move around in the city, you may need several links at the same time, so that if one link is blocked, you still have two others to survive. So that needs to be up and running in the network. And again, you need support for compute services and AI functionality. So you need to process all that data. That there will be a lot of data collected throughout the city. You need to build a map from that, and using that map, you can navigate different robots in the city, and that could be a lot of robots. Of course, you can't do that manually. You have to use some sort of intelligence in order to navigate these robots. So that's 3 examples of what we would like to do with 6G. So that would answer, at least from my point of view, what's the point. And I hope that you got the feeling that this is not so easy to do. To some extent, we can do some things already with 5G, but in 6G, we can design it from the start to have these different parts in. Can design it to have the compute part in, the sensing part in, this dense functionality, multi-link functionality, satellites, etc., in from the start. So that's what we're aiming for, and that's sort of is the point. How are we with time? We still have.
Yeah, that's 20 more minutes. So it's
I have
no
20
rush.
more minutes. Wow. Finally, then, how to do 6G? That's sort of the favorite topic if you ask the radio network people. But maybe you will not enjoy this as much. But I don't know. I don't have so much material on this one. If you want to know more, please ask questions. So I would just say something on a rather high level, that when we think about what we want to do with 6G, and when we think about where we are with 5G, we see that the delta is a set of capabilities that we need to work on. And here we have created a map of these capabilities in two sort of rings and a central point. And this inner ring, that's capabilities that we have already worked on in 3G, 4G, 5G for a very long time. And these are the classical networking capabilities: mobility, data rates, latency, capacity, etc., coverage, energy performance, and also positioning. Maybe not a super classical one, but at least in 4G, since 4G, we have worked on positioning. So that we want to continue enhancing. That's more or less business as usual. In this outer ring, we broaden the network. So that's addressing this beyond communication networks and the 6G platform things. Here we want to do more than in the classical networks. We want to ensure privacy through network functionality. We want a high versatility of deploying services so that you can define services dynamically and get them delivered by the network. We want to ensure service availability and a high resilience of networks. And we want networks to be easily deployed, so you can just throw out nodes anywhere and they would just automatically connect to the network. That's the wet dream of network deployment. And of course, we want, again, this compute functionality, AI functionality. We want this network sensing to be there. And these 6G capabilities are then addressing both this communication beyond mobile broadband, making a better bit pipe. That's the blue part, and more or less everything relates to that. But we also have this beyond communication, the 6G platform, providing new types of services, and the outer part relates to that, adding new services on top of the current network functionality. And these are all then the targets for the new technology that we work with in 6G. And the areas then that are addressing these targets, that should in the end deliver these capabilities. That's 8 different targets, and at the center we have this important goal of providing efficient, secure, and sustainable solution. That's sort of obvious, you could say. Of course, we want to do that, and we have worked on it in every generation. We will continue to work on it. It's still important, right? Working with energy performance, making networks even more efficient from a communication perspective, from an energy perspective, from a deployment perspective. They need to be cost efficient, of course, so that you can provide networks to as many people as possible. That's important. And of course, they need to be sustainable, not only from an energy perspective, also they need to be materials efficient, etc. So there are many aspects there in the center that, of course, we will address. So starting from here, we will work on extreme performance and coverage. So you saw that several of the use cases, they need higher data rates and higher capacity. So we do that by simply adding more wireless bands and also, of course, improving the performance of the existing bands. So for 6G, we look at maybe 7 to 20 gigahertz bands. So the lower, the upper midband, I think it's called. Or is it the lower midband? Upper midband, yeah, you want? Upper midband, yeah. So simply using more spectrum for mobile communication. We're also looking at very high frequencies, like 100 gigahertz. That's called sub-terahertz. It's been quite popular in academia for quite some time because it's new and exotic. We see that as a possible complement for short-range communication. Maybe here in an office space like this, you could use sub-terahertz. Maybe in factories, etc. And that probably requires a rather dense network. Of course, we like that. We like dense networks. We want to have very trustworthy networks, and so we work with all sorts of security solutions. We work with network resilience, and that's a very important and difficult area where you look at all the parts of the network, and the networks can be very big, right? And then you need to collect information from all parts of the network. You need to analyze that information, use that for prediction of how the network will perform in the next hours or in the next day, and you try to see if there are patterns that you can detect that would indicate a coming failure of a node. Some node is starting to behave in a strange way, and you sort of route traffic around that node then. And then you sort of never go into a failure state. You avoid it by going around it. So using a lot of data, that's sort of our flavor of big data crunching, you could say. You collect a lot of data, you crunch it, and then you make decisions based on that. Network compute fabric, I've already talked about that. Making the network a big computer, so you can use you can do computing pretty much anywhere. We talk about ubiquitous computing, fluid computing, so that you can move compute tasks from any network node. So from your device, let's say that you have a XR headset or these smart glasses. They are very thin clients. They don't have very much battery power. They don't have very much compute power, but they do have a link to the network, so they can stream their data, their vision that they see, the capture from the glasses. They stream that to the network. The network is doing the number crunching in the edge nodes, so the closest nodes, and then you send back the model, the digital model that you should see. So the video stream that the user should see. That requires quite a lot of processing capabilities in the network, and also, of course, very good links between the nodes and the devices. Joint communication and sensing, I mentioned that in several times. So basically doing radar sensing with the radio interface. So either you can try to analyze the reflection of the data packets that you send. That would be the smartest way you could see. Probably it's too smart, right? It's kind of difficult because then you have to it's simply challenging because first of all, you don't always know when the data packets will happen, and it's harder to analyze. So better than to send a specific symbol, so you know that you send a certain probe signal every now and then you listen to the reflection of the probe. That's challenging because in principle it would require you to do full duplex. So you would need to be able to transmit and listen at the same time. Otherwise you would be blind in the closest area, right? So if you have to turn off while listening to the echo, you wouldn't be able to see the closest area, right? So you can do it in other ways. You can listen to transmissions from other nodes or from devices themselves. So if the devices send a ping and that's reflected on some object close to you and you listen to the ping, then you can sort of build up a model of the surrounding. But it is very difficult, and you probably need a lot of links, and you need to see all the links, right? So you can't have objects in between. You have to have line of sight in order to do that. So you need probably a rather dense network in order to do this as well. So in many ways, several of these technology areas point at the need for a denser network. So you need a higher density of network nodes. And we see that we want to embed devices everywhere. So that's working on these zero energy devices, for instance. So small, cheap devices that have a very small form factor. They're very thin. Maybe they're stamp sized, and that harvest energy from the surrounding that you can put on everything. And they can be embedded into anything and used for localization. Yes, I think I will stop there and not go into more details. And if you want to understand more, you can look at our white paper on 6E. And otherwise, you can email me. Thanks.
Yeah, thank you, Gustav. Very interesting to hear all about this. So we can start up for questions, and maybe I can just start it off. In the beginning, you show this sort of exponential growth that you often see.
Yeah.
And I don't know the rate of this growth, but you add a zero every generation of the sort of the number of nodes or the number of devices.
So we recently had this report, Ericsson Mobility Report, and I think the current rate is 3 times increase in total traffic volume in the coming 5 years. Mm-hmm. So 3 times in 5 years. Yeah. That's the current rate.
I was sort of interested in how you see it now. I mean, in the beginning, things can grow exponentially and often does. But at some point, you reach a limit, physical limits, energy limits. You run out of devices that could be connected. So where do you see the end? I mean, so how far will this get? How dense will the network?
I think the current frontier is perhaps this energy limit. We see that if we just take the current technology and deploy lots of that, it will consume a lot of energy, too much energy. We need to be more energy efficient. So once we are very energy efficient, if we have these zero energy nodes, and if our networks nodes don't consume as much energy as they do now, you could densify a lot more. You could make the network itself maybe 10 times denser than today. And you could at least have 100 times as many connected devices as today.
And do you think we will make value of all of those connected devices?
Yeah, I mean, that's up to you. I mean, I hinted at some transport related ones. Then there are of course many other use cases that you can convert into value. That's our hope. But in the end, I mean, we provide the technology and we hint at sort of the usage, but the actual usage, it's very hard to construct. It will sort of appear over time. And with smart startups and academia and maybe big industry players that will try out the technology and see what it can be used for.
And I have another question. I mean, we work a bit with this of connecting the situational awareness and connected vehicles, real-time applications, safety critical. And then we want to understand how much the network can be part of that. Can we lift intelligence outside of the vehicle, and can we sort of remain safe and secure? And you have addressed this as well here. But when we talk to the automotive industry, to me at least, it seems like they are adapting a little bit to sort of trusting algorithms and AI and so on that they put in their own devices,
Yeah.
in the own vehicle. But when you talk about adding network to this, then they're still more afraid. So they're trusting more AI in the vehicle than they are trusting the network.
Oh, okay, so they want it localized.
Yeah, so local, and
yeah.
it's, I think it also has to do with maybe liability. I mean, if you need to put the network into that as well, will the network be liable for the functionality of the vehicle?
Yeah.
So what's your thoughts on this?
And it is challenging. I mean, for 5G, we talked a lot about industrial automation. It has been a tough journey, I think, to convince industries that they should use wireless networks and that they maybe should rely on a centralized network somewhere. Even though that's more cost efficient, they often want their own sort of solution local with cables and a local compute node to handle the functionality. So it is a question of trust, and I think we need to prove that it works with different proof of concepts, and that's being worked on already now. So I think to convince people to use 6G more in more scenarios, like in the transport, we need to build it and show it, and that I think that's going to happen. And then, of course, we need to point at the benefits. I mean, the cost efficiency, the saved life that you can get from connecting cars and drones and getting this updated real-time map. I mean, you can principally can avoid all types of collisions if you do this fully, and that's pretty good. That's worth. That's worth relying on, I would say. But I think,
do you
yes.
think we build in vulnerability and talk about resilience, sort of the societal resilience? We depend on. I mean, we depend on a lot of things already.
Yeah.
But, we would any more depend on the network. Is that the problem?
It is a challenge, I would say. What we're saying is that, okay, put everything in the network, or many things. Put all your functionality there, and we will provide it through the network. And then you need to, of course, make sure that the network is resilient enough. So that's the current challenge. So the network can never break, in a sense. Of course, if the power is out, the power is out, and if internet breaks, then it's hard to do it something. But as far as it's possible, the network should survive any type of challenging events that would happen. So it should be really resilient and rely on this. You could say it's the internet principle, right? So if you have many nodes and many links between the nodes, even if you remove half of the nodes, you sort of take them out, the network as such would still survive, right? Because you have enough links. So that's the principle that we would use as well to ensure resilience. And then, as I mentioned, I mean, prediction is an important tool. There. You should make sure not to end up in a situation where you could risk functionality. You should predict it and then act before it happens. It's a challenge, but it's a very good question, and it's a difficult challenge, I would say. Making people trust the networks. Yeah.
And make them trustworthy.
And make them trustworthy, yeah.
Are there more questions?
I think that we'll have to wrap now because we're out of time.
Unfortunately.
Final question. Yeah. I mean, I think a little bit. Can you say something about how do you think this will change how we do research in industry and in academia, and how we do research across disciplines?
Yeah, we have engaged now in several large EU projects where we have the ambition to work more cross-discipline. We are, for instance, then addressing this sustainability challenge by also inviting people from other disciplines. So, for instance, the social sciences are now being involved in our research projects. So it's not only a technical problem, It's also a problem of how people think about technology, how people use technology. And we also have, techno-economical aspects. How can we make sure that our future networks are not only for the rich people in cities? How can we make sure it's deployed everywhere? And for that, you need other disciplines involved. So we are broadening the scope a bit. And when it comes to other engineering disciplines, I think you have been in for a long time. So maybe no change there, but probably more of the same. So working with other technology disciplines apart from radio networks.
Okay, I guess we then wrap up and thank Gustav Wikström again for.
Thank you. Thanks for inviting me.
Thank you.